Hi there. Today we'll be talking about the Earth itself and why organisms live where they live on this Earth. So, when we look at that figure that I showed you of the hierarchical relationships of biological levels from lecture 1, we learned that ecosystems, the sum total of all the ecosystems of the Earth, make up the biosphere. Right, so when we're talking about the biosphere, what we're really talking about is the living Earth. And studying the biosphere, we have to understand all the factors that play into why organisms may live where they live. Right? This field is called biogeography because it combines biology with geography and geology. Right? Because we need to understand a little bit about why organisms can live where they live. If you look at a map of the Earth and the organisms that are distributed there, you're going to see that there are certain similarities in habitats. Right, you're going to see, for example, that all of the tropical rainforests are located roughly the same latitudes. All the deserts are located more or less the same latitudes. Right, so certain climatic conditions will favor the growth of certain types of what are called biomes. So the term biome here refers to a particular type of vegetation and community type. So, for example, if you were to be kidnapped and you were put in a van and in an airplane, and after hours and hours and hours of travel, you were really disoriented, your kidnappers take you to a place and they take the hood off your head, and you notice that the place is very hot and it's very humid, right? To you, you really immediately deduce that you are in a tropical rainforest, but you wouldn't necessarily know whether you were in Brazil or Congo or Indonesia. Right, so that's what I mean by biome, a certain vegetative type. Now, the species that are in the Congo and Indonesia, they're not the same species, but there's a particular type of set of conditions that we associate with tropical rainforests, right? And that's what I'm referring to by biome. Now, obviously, the factors that dictate what can live in a given area depend on the region's climate, right? So the overall weather conditions of the area, the climatic conditions of an area, will determine what can grow. So the term climate refers to what are the overall average conditions throughout the year. When we talk about the weather, we can say that the temperature is this and the precipitation is this. But when we take measurements over the course of many, many years, we can get a better sense of an area's climate. And so fundamentally, in order to understand the distribution of biomes throughout the Earth, we need to understand some of the factors that determine the climatic conditions of that area. Right? And just what may or may not be obvious to you is that this is a very difficult thing to do, right? Modeling climate. And we're not going to solve the answers to climate in an hour. What I really want to give to you is just a sense of some of the factors that go into determining an area's climate. And they're relatively obvious, right? Like how much sunlight an area gets, how much precipitation. Those are the factors, the major factors that determine climate. All right, so in order to understand, in order to start to understand climate variation, regional climate variation, we need to understand a couple of things about the physical properties of the Earth. Right? And the first and most important is that the Earth is round. Right? Now, at first glance, this may not seem all that important. Right? But if we have two beams of sunlight, A and B, right, and because the thickness is the same, they have the same amount of energy. Now, beam B is going to hit the Earth right at the equator. And you can see that that beam's energy is going to be distributed over this much area. Right? Beam A is going to hit at a very high latitude, but because it's a very oblique angle, that same energy is going to be distributed over a wider area. Right? So same amount of energy over a wider area means that per unit of area, there's going to be much less energy absorbed. Right? So what the net effect of this is that it's hot at the equator and cold at the poles. Right? And I think this is something that we all understand, but the reason why that is because the Earth is round. Right? Second thing is the Earth is spinning, going around and around and around. Right? And it's that rotation of the Earth that's responsible for day and night. Now, third thing to understand is that there's a little bit of a tilt to Earth's axis. It's about 23.5 degrees. Right? But it's that tilt that gives us the seasonal variation. Right? In June, the northern hemisphere, the North Pole, is tilted towards the sun. Right? So this distance is about 93 million miles. But that northern hemisphere, the North Pole, is tilted towards the sun. So if you live at a very high latitude, let's just say Greenland here, this will all be day, and then your night is actually relatively short. So the days are long, the nights are short. Overall, it's going to be warmer. This is a condition that we call summer. Right? So it rotates and rotates and rotates and rotates as you move around the sun. In winter, in December, that northern hemisphere is going to be tilted away from the sun, which means that all of this is night and only this is day. So the days are short, the nights are long, overall conditions are cooler. Right? This is something that we call winter. Now I want you to note that when it's winter in the northern hemisphere, it's actually summer in the southern hemisphere, and vice versa. Right? And it's basically simply a result of the tilt of the Earth. So everything I just discussed is a little bit not 100% fixed in stone. There are a little bit of irregularities, right? Sometimes we are a little bit closer to the sun, sometimes a little bit further away. Right? We're not exactly in a perfect orbit around the sun. We're not exactly 23.5 degrees. Sometimes there's a little bit of a wobble. Right? All these little wobbles and little irregularities in Earth's orbit around the sun means that there's a varying amount of solar radiation that comes in. And this has been responsible for past climate changes. You can see that there have been glacial periods and then interglacial periods. Right? So historical climate change has been driven by these little irregularities in Earth's movements called Milankovitch cycles. All right? So, moving on. So we know here that the equator is the warmest part of the Earth, and the poles are the coldest. Now, that irregular distribution of thermal energy means that the air is going to move in relatively set patterns called convection cells. So I'll draw it over here. So I'll leave the figure up here, but I'll draw it on the side here, a parallel. So this is the equator, 0 degrees. At the equator, the air is going to be very, very warm because that is where the temperature is the highest, and warm air will rise. And what happens when it rises is that it'll cool off. And then once it hits the stratosphere, it'll peel off to the north and the south and ultimately descend and then rotate back to the Earth. So these circuits that you're seeing over here between 0 and about 30 degrees north latitude and about 30 degrees south latitude are caused by the fact that there's warm air at the equator that's rising. It peels off when it hits the stratosphere, and then basically runs out of energy and descends around 30 degrees. So there's a regular distribution of air, circulation of air between 0 and 30 that moves like so, right? moving towards the poles, the wind that comes off the poles is extremely cold. And as it approaches the 60-degree latitudes, it gets, not, I wouldn't say exactly warm, but relatively warmer, and then will rise, and that air will then go back to the poles. And so this is why you see these circuits of air at the poles going in the same directions as the ones between the equators, the equator and 30-degree latitude. Right? And what happens in between is the opposite. This rising air at 60 degrees will cause the air next to it to rise, and this descending air at 30 degrees will cause it to descend. And so between 30 and 60, the air moves in the opposite direction. Right? In the south, this descending air causes that air to descend, and this rising air causes that air to rise, and you'll have a circuit of air in the opposite direction. These are called convection cells, right? And under normal conditions, this is how the air will circulate. And again, this is because it is all driven by the fact that it's warm at the equator and cold at the poles, and that is driven by the fact that the Earth is round. Now, the movement of air is really important because it's also one of the components of air is water vapor. And so this movement of air is really also about the movement of precipitation. And one of the things you're going to notice is that right along the equator, it is very, very rainy. And it's because here at the equator, this air that's rising, is very laden with moisture because the Earth is mostly covered in water. So this very high amount of solar radiation means that this air is going to be hot and humid. And when it rises, it cools, and that same that same water is going to come back down at the equator. And this is why you're going to see at the equator it's going to be hot and humid and also rainy. And this is why all the rainforests are located in that band around the equator. Similarly, at 30 degrees north latitude and south latitude, this is where the air is coming down from the high altitudes. So the air pressure will be high, but that air pressure, the air that's coming down at 30 degrees north and south latitude, has been in the high atmosphere. Right? So there's very little precipitation. So what kind of climates are determined or characterized by low precipitation? Right? Those will be where the deserts are, right? Roughly 30 degrees north and south latitude. And you'll see that means the Sonoran Desert over here, Sahara Desert, the Middle East, the Gobi Desert, Australian Outback, the Kalahari and Namib Deserts in southern Africa, and the Atacama Deserts in Chile. Right? They're all located roughly 30 degrees north and south latitude, and that's because this is where the air is extremely dry.
To an observer above
Now,
the
the Earth
merry-go-round,
itself is
the
also
path of the ball
spinning.
appears straight, while to someone sitting on it, the ball appears to curve to the left. This exemplifies the Coriolis force, whereby, to an observer on the rotating Earth, the path of an object appears to be deflected, and this is a result of the Earth's rotation.
So the Earth is spinning as well, which means that the linear paths that you see are actually going to curve a little bit. So going back to this, let's do this. If you are standing at the surface of the Earth at, let's say, 15 degrees north latitude, because of the convection cell, you would expect the wind to come straight from the north. Right? So looking at it in 3 dimensions, the air rises here, goes to 30 degrees north, and comes back down. Right? So at the equator, at the surface of the Earth, you would expect the movement of the air to be from the north. Right? From 0 to 30 south, you would expect it to be from the south, etc., like so. And so these arrows are basically like if you're a person like that, sorry, forgive my drawing, if you're a person on the Earth, because the arrow is rising, then coming across, then coming down, and then going back to you, right, the air would be normally coming from the north. Right? If you're a person standing right here, the air would be coming from the south. If you're a person standing right here, the air would be coming from the north. Okay? And it's because of these convection cells. Basically, we're talking about what's happening at the surface of the Earth because of these convection cells. The problem is there's rotation. And when there's rotation, we have to consider something called the Coriolis effect. So imagine there's a turntable here. And as this record spins around, that we put a green line on this. And there's point A and point B. Now, what this is going to look like is that the line is simply going to be going around and around like hands on a clock. Okay? However, point A and point B are actually not traveling the same distance. The same speed. Right? Because B has to go all the way around the fattest part of the record, whereas in the same time, A is only going around this distance, B must be going faster than A. So why is this important? Because when you consider the fact that the Earth is round, it means that all of us on Earth are actually moving at different speeds. These guys at the equator are going around the fattest part of the Earth in a single day, whereas these guys are going around making a smaller loop. Okay? So what? People are moving at different speeds. Alright, when we're talking about two things going at different speeds, the frame of reference between them means that if we just look at a moving object relative to the frame of reference, that object and that frame of reference won't match up. Right? You can see from this video here.
To an observer above the merry-go-round,
the ball
path
looks
of
like
the
it's
ball
moving
appears
straight.
while to someone sitting on it, the ball appears to curve
But when
to the
you're
left.
on it, it curves. Right? So we have already established that B is going faster than A. Now imagine that you are on A and your friend is on B. As you're spinning around, all you see is your friend and this green line. So as you're going around, your friend and that green line are all moving at the same speed. So it does not appear to you that you and your friend are moving at a different speed. Right? But as you try to roll a ball from A to B on that line, as the ball rolls towards B, your friend is actually moving away faster than you are, right? You're only traveling this far, whereas your friend on B is traveling a little further distance, greater distance. Right? What this means is that relative to this green line, relative to the green line, that ball is going to peel off to the left. Right? Imagine that you're looking from A, it's going to peel off to the left. Okay? So why is this important? Because we've already established that if you're a man standing right here, or a woman standing right here, the wind should be coming from the north. But because this point is moving faster than this point, the air that as it moves from, we'll call this point A and this point B, as it moves from A to B, it's not moving fast enough, right? So if our frame of reference is A and B, what will actually happen is the air will bend off to the west, right? In a similar way, the air that should be coming from this point to this point from the south actually will bend off to the left as well, right? From this point to this point, right? They'll bend off to the east, like so. Okay? And it has to do with the fact that the Earth is round, and that's where these convection cells are coming from, but also that it's rotating. So this movement of air, as it moves across the surface of the ocean, will actually drive ocean currents. So imagine that we have air moving this way between 0 and 30, right? And this way between 30 and 60, pushing the water, I mean. If that's the case, then what we would expect, if those are our only driving forces, we would expect the water to be moving clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. So that prevailing movement of air across the surface of the water will cause that circular movement of water. These circular movements of water are called gyres, Gyres. And there are 5 major gyres in the world's oceans. You have the North Atlantic, the South Atlantic, North Pacific, South Pacific, and Indian Ocean gyres. But the thing that's important to understand is that the water will move clockwise in the northern hemisphere and counterclockwise in the southern. And you can imagine this is going to have very significant impacts on biodiversity, right? We tend to think of the ocean as one big entity, right? And even if you don't think of the oceans as one big entity, you would think at least the Pacific is one big entity, right? But you can see that the oh no, I've lost my laser pointer. Right? That the North Pacific and the South Pacific are actually 2 separate oceans, realistically, because the water is moving in circles like that. All right. So why is this important? Because this impacts climate. Right? This is Scotland. Nice place. That's Alaska. Nice place, but you wouldn't want to farm there, right? So why is it that you can farm in one place and not the other? When, if you look, Scotland and Juneau, Alaska are roughly on the same latitude. So why is Scotland so much warmer than Juneau is? It's because of this movement of water. Right? So because the water is moving clockwise in the northern hemisphere, the warm water off the coast of Liberia moves up here and then gets carried up here to northern Europe. And as that warm water moves up here, it gives off heat. And that's what keeps northern Europe relatively warm. Why doesn't the same thing occur in Alaska? Because the water's moving in a circle. It's cold, cold, cold. Right? It's basically bringing all of its energy over here, right? Causing hurricanes and typhoons over in Southeast Asia. Comes up here to the North Pacific where it cools off, and that's what Alaska is getting. That's not the only movement of water, right? There's deep water ocean currents as well. If you've ever seen Finding Nemo and they were looking for the EAC, right? That's a deep water ocean current. It's a deep water ocean current. Right? And that deep water ocean current is actually driven by the movement of water at the top, at the surface, in what's called thermohaline circulation. So we've already established that there's a clockwise movement of water in the North Atlantic, and as it comes up, it starts to get cooler and cooler and cooler and cooler, and then as it cools, it becomes denser and it sinks down here. Okay? Now the irony is that one of the scenarios, the nightmare scenarios that people are predicting, is that global warming can actually ultimately lead to an ice age. One of the big problems is over here in Greenland. All that Arctic ice is melting into the Baltic Sea up here. And so as this water is coming up, and it should be subducting, going under, it can't anymore because even though that water is super cold, it's also fresh water, which means this water can't subduct anymore. If that's the case, then this whole Gulf Stream will back up. And if that does, there's no more warmth being carried over here to Northern Europe. That means this whole northern part of the continent will ice over, and that may ultimately plunge us into an ice age. All right? So what you can gather is that there's a lot of things that what we're talking about are large-scale conditions that lead to climatic conditions of a given area. Now, local features can also impact climate. Right? We have these here in California. One of the things that we have noticed in California is that on a hot day, you'd rather be at the beach than in Riverside, right? And the reason why is on a hot day, right, the land gets warmer than the air. Land gets warmer quicker than the water does, and that causes that air to rise, and that would be replaced by a sea breeze. And this is why a beach is a great place to fly a kite. Right, and the opposite is true on very, very cold nights, right? Because the water retains its heat much better than the land does. So it gets really cold on land, but that water will radiate heat back to shoreline communities. We also have mountains in California, and this will lead to a condition called a rain shadow. So imagine that there's air coming off of the ocean, and this air that's coming off the ocean is pregnant with moisture because it's been over the ocean for a long time. All right, so it's very, very there's a lot of water vapor in there. As it starts to climb a mountain, like the Sierra Nevadas, what ends up happening is that it cools. And so on the windward side, as the air cools, it will lose some of its water. And so the windward side of the mountain will be very, very rainy. But by the time that air gets over to the leeward side, it's very, very dry. And this is why you would expect on the windward side, very, very lush vegetation, lots of rain, and on the leeward side, lots and lots of it's very, very dry conditions, arid. Right? So this is what's called a rain shadow. These deserts that sit on the leeward side of mountains are there because they sit in the rain shadow of the mountain ranges. So if you've ever been up to the Sierra Nevadas, on the western side, this is where you have Sequoia and Kings Canyon, Yosemite, John Muir Trail, a lot of beautiful forests on the western slope of the Sierra Nevada. And in fact, the tallest trees in the world are here in California on the western Sierras. Because, they are watered by the Pacific Ocean, the biggest water source on Earth. So it makes sense that the largest trees would be here. On the other side of the Sierra Nevadas, what do you have? You have Nevada, right, which is it's absolute wasteland. It's a desert because it sits in the shadow, the rain shadow of the Sierra Nevadas. So, both local and large-scale climate patterns govern what can grow in a given area, right? Depending on temperature and humidity or precipitation in an area. Those are the things that will determine what can live in a given area. Right? So the distribution of biomes is fundamentally determined by the distribution of climatic conditions. So for the next couple of minutes, we'll just discuss these different types of biomes. So I expect you to know the descriptions of these biomes and what the general conditions are for all of these. Most of them are pretty obvious, or you know them already. So starting from the highest latitudes, the tundra are the highest altitude or highest latitude biomes. They're very, very cold places, very, very windy. Right? In fact, so cold there The ground is permanently frozen in a condition very cleverly called permafrost. Because the water in the soil is frozen, there's very little tree growth. Moving down a little bit, you have the boreal forest or the coniferous forests. This is called the taiga. These are forests with lots and lots of conifers. Deciduous forests are trees that will lose their leaves in the winter. Grasslands are generally, there's not enough rainfall to support a lot of tree growth, and this is where grasses grow, obviously. These are mostly all gone in the world because they've mostly been converted to agricultural lands. Right? Most of the crops that we grow are grasses, right? Evolutionarily, right? The corn, wheat, these are all grasses. So the best place to grow them, obviously, are grasslands. And so this is why most of the grasslands have been converted to agricultural lands. The chaparral, this is where we live. This is where we live, right? So these are mild climates. Typically quite dry, not a lot of precipitation. High danger of fire. Deserts are a biome that's characterized by its low precipitation. Right, we tend to think of deserts as very hot places, but in fact they can be very hot and very cold as well, right? Because there's no water vapor in the air, there's when it's hot, it's really hot, and when it's cold, it's really cold. Remember how we discussed that water is very highly resistant to temperature changes? So if your air has no water, right, you're going to have very extreme temperature variations. And then tropical forests are hot and humid places, lots of precipitation, and therefore a lot of tree growth, right? You have a lot of sunlight, you'll have a lot of water, you'll have a lot of tree growth. Right, now interestingly, these are the richest places on Earth in terms of biodiversity, but ironically the soils are really poor, right? Largely because all the nutrients are in the trees themselves. So one of the phenomena that's happening right now is that these rainforests are being cleared to establish farms. That's kind of a bad idea because the soils are so poor. So what the farmers are doing is they're cutting down these trees and they're burning them to return the nutrients back to the soil. But that's not a viable long-term solution because the rain will cause those nutrients to leach out of the soil. So the next year you basically have to cut another patch of the forest and burn it. Right? It's called slash and burn agriculture. You have to slash and burn another section in order for your farm to grow. Right? And then the next year another patch and another patch. And this is why tropical forest degradation is so severe. Not to be outdone, marine biologists are also like, hey, this water is not one habitat. Right? So they divvy up the waters of the earth into distinct biomes. The major division is between freshwater and marine environments, right? The ocean versus lakes and streams and stuff. So lakes are basically depressions in the earth where water can accumulate. Right? And they're connected to each other via streams and rivers. Right? Lakes can either be oligotrophic or eutrophic. Right? Oligotrophic, these are clear waters that are high in oxygen but low in nutrients. Right? And just by looking at the description, you would think that the oligotrophic lakes are unhealthy and the eutrophic lakes are healthy, right? Because the eutrophic lakes are rich in organic matter and nutrients. Right? However, it's the opposite. Right? So eutrophic lakes, what happens is they're polluted with nutrients. So as nitrogen and phosphorus runs off from the land into the streams, right, the amount of nutrients is so high that the algae build up. And so now you have a Magillian algae. The problem with algae is that they die really, really rapidly. They only last a couple of days or so. So once you have a Magillian algae, and these guys are all reproducing like mad, you're also going to be producing a huge amount of dead organic matter. And then what ends up happening is the bacteria become very, very plentiful. And when the bacteria become really plentiful, they suck up all of the oxygen, and then all the other organisms die. So eutrophic lakes, they're rich in organic matter, but they're very low in oxygen, and in fact support very little other life. And so water pollution can very commonly cause a lake to become eutrophic. There was an experiment that was done. It could never be repeated in modern times. But it was a very famous experiment where an ecologist found an hourglass-shaped lake. And on this side of the lake, he put carbon, nitrogen, and sulfur. And on this side of the lake, he put carbon, nitrogen, sulfur, and phosphorus. And you can see that this water is very eutrophic, whereas this one's still oligotrophic. And the conclusion was it's typically phosphorus that is the limiting factor for algae growth. So eutrophic lakes are typically so because they are contaminated with phosphorus. Oceans also have very unique biomes. So the oceans can be divided up into the coastal regions and the oceanic regions. So the coastal regions are near the shore, where the water depth is not particularly deep, whereas the oceanic regions can descend to extremely deep depths. Right. The intertidal zone is the place between the high and low tide. Okay. Then we have the benthic zone, and this is anywhere along the ocean floor. So whether you're talking about coastal region or whether you're talking about the deep ocean, any creature that lives on the floor of the ocean belongs to the benthic zone. Right. The opposite of benthic is pelagic. So if you swim around, you're pelagic. If you're walking around on the floor, you're benthic. Right. The marine ecosystem is also divided into the photic and aphotic. So only in the upper layers of the water can light penetrate. So photosynthesis can only occur in the photic zone. Right. The deep water is very, very dark, right, and that's called the aphotic zone. So the ecosystem structure is very, very different in the photic zone versus the aphotic zone. There's a phenomenon called upwelling that's really important in coastal communities. What scientists have discovered is that coastal regions are much, much more biodiverse than the deep ocean. And it's because of a phenomenon called upwelling. So the nutrients will fall down to the bottom of the ocean, but because of the Coriolis effect, this wind will cause that top layer of water to peel off. And when that top layer of water gets peeled off, it gets replaced by the water from underneath. That's called upwelling. So this nutrient-rich water will come up to the surface. And now you have the nutrients with the photic zone, and this is how you get algae growth. And the algae growth is the primary productivity, if you remember that term. So if you have a high degree of primary productivity, you can sustain a lot more life. And so this is the reason why coastal regions are more biodiverse than deep water regions, because there is upwelling that brings nutrients to the surface. Periodically, we have a phenomenon called an El Nino event. Now remember, we discussed that water normally flows clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. What this will do is this rotation will cause this upwelling on the western coasts of the Americas. For reasons that are not well understood, in El Nino winters, the trade winds go the opposite direction. Right? And so what will end up happening is that there will be much less upwelling, fewer nutrients coming up to the surface, and therefore less algae growth and less fish. But what this does is also bring storms over here to Southern California and the western coast of the Americas. Right? So whereas normally the that thermal energy will be carried over here to Southeast Asia and northeastern Australia. In El Nino years, it's carried over here to western Mexico and the western U.S. and the western Peru, Ecuador, Chile. So the phenomenon was first observed by Peruvian fishermen because they weren't catching any fish, and so you don't have any plankton in El Nino winters, right? Whereas you can see a big abundance of plankton in normal conditions.